Alright guys, back to work. So, we were talking about binary relation. Andrew asked it. And I think we went through the 4 properties. Reflexive, symmetric, transitive, and anti-reflexive. Yeah? So should we move down? Inverse and composition. For function, the inverse of a function is a complicated thing because the function has to be bijective to have an inverse. And bijective means injective and subjective, and we add conditions. For a relation, the inverse is a piece of cake. If you have a pair x, y in the relation, and the inverse flips it over. You have y and x. And we call this inverse. Classic example is the parent to child and child parent. The inverse is child parent. Yeah? Composition is a little bit more complicated. So let's look at an example. So to make the example, to make the composition, we need 2 relations, R and S. Since we consider binary relation, the set is the same for all the elements here. In principle, we can do the composition also if the elements are not, if the sets are not the same. And so here, suppose that you have x related to y and y related to z in S, then the composition R composed with S is what? X Z. Should we make an example? So, suppose that in R we say R is defined in this way. Is the pair xy natural such that x and y are natural number. And y is equal x or x plus 1 or x plus 2. I'm writing this quickly, okay? So, let's see the example of some elements that are in this relation. You want to tell me some pairs in this relation? 2, 2, 2, 3, 2, 4, 3, 3, 3, 4, 3, 5. You understand? This is just the definition. Yes? So now let's do S. We say S is the set x, y such that x and y are natural numbers again, and x is less than y. Alright? It's the usual less than. So who can tell me a few elements that are here? 3, 7, 3, 19, 4, 5, and so on. The second has to be bigger than the first. Yeah? These are not particularly interesting relations for anything except for this example. So what is the composition R composed to S? Who can tell me some elements that are there and some elements that are not? Yes, said, look, here I have 2, 3, which is in R. 2 and 3 are related in R. Thank you. And then I have 3 and 7 are related in S. 3 and 7 are related in S. So what I conclude, 2 are related in the composition. Three, 4, and 4, 5, yes. So 3 and 5. They were already related in R, and they are also related in the So, because here I have 3, 2 and 3 are related for R, and 3 and 7 are related for S. So, the first one here and the last one here are related in the composition. Yes?
The two relations of systems, like if it's R composite S, it should be S first then R.
Oh, did I flip it? Maybe. So, some books do in one way and some books do in the other. So let's see which one is done here, and if I got it wrong, we correct it. All right, the composition of relations. All right, so here says 3 sets. This is the case in which the sets are not necessarily equal. So R is from A to B, and S is from B to C. And so here, yes, you are right. So here is done in the other way. So here we are changing. Oh, sorry, you are not seeing this one. You didn't complain. So here the relation is R is from A to B. So, but here writes it in a different way. So I think what I said is right. Do people agree or not? So here the first that I pick is R and the second is S. And so here instead the composition is SR, but I am doing RS. So this looks different because I pick the different names than they are here. So here we have R that is from A to B, and S that is from B to C. So here I have this one is in A, this is an element of A, and this is an element of B. Yes, but I want to see that one. So this is an element of A and this is an element of B. Yeah, you are right. The book is doing it the other way. All right. All right, so I think...
So what would be 3, 7, and then 3.
So now we can try to do it again with the other notation, but I changed the names. So here I have the relation S. You can see that. Let me try to be consistent with the book. So here I leave it at the same. I leave the same, but I do the composition in the other way. So this one is S composed to R, and is S composed to R. And so here I have S composed to R, in which I do first R and then S. So some authors do this differently, because when you read it, say it again?
It makes more sense the other way.
Well, so we have to be consistent. So sorry, we go with the book, and what I did, just we have to write it the other way.
Or the solutions, what you have there? Or
Yes, because now I changed the names, so I do it the other way. So to do what I want here, I should have written S composed to R rather than R composed to S.
for the solution.
Yes, remain the same. All right. So we did the composition and the inverse. So what is a partial order and what is an equivalence? Someone wants to give it a try? So the equivalence is a relation which is reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. So let's take an example. Let's say that two pens are equivalent if they write the same color. So this one writes blue, this one writes blue, this one writes sorry, you don't see it, orange. Oh, was it right? I had too many screens here to know what's going on. This one writes black. And this one writes blue. So, why this is an equivalence? Because if a pen writes some color, say blue, that pen writes the color blue, so it's reflexive. A pen writes its own color, right? Of course, see. If pen A writes a color and pen B writes the same color, then B writes the same color as A, so you can flip them. So it's symmetric. And of course, if one pen writes blue and this one writes blue, and this one writes blue, and this one writes blue, then the first and the last write blue. And so, This is a equivalence relation. Two pens are equivalent if they write the same color. What are the equivalence classes? Well, we have one of all the pens that write blue, one of all the pens that write black, one of all the pens that writes red, and so on. These are the equivalent classes. What is a property? That if you put together all the equivalence classes, if you do the union, you get all the pens that I have. If you pick one pen in one and one pen in another, there is no chance that you pick the same pen. They are disjoint, completely apart. Equivalent classes. And you would represent them with a color. Many times when we say that things are equal, we mean that they are equivalent. Right? If you take two coins and they are two quarters and then you say that they are equal, they are not equal. If you bend one, the other one doesn't get bent. If they were equal, you bend one, they both are bent because they are the same. Alright? When we say that 2 plus 2 is equal to 4, it's not really exactly true. If you want to represent them in a computer, you represent them very differently. So when we say that they are equal, we say they have the same value. And with the money, we say, well, they are the same amount of money. All right, so much for equivalence. What about the partial order? What is the partial order?
Reflexive, antisymmetric, and transitive.
Fantastic. Reflexive, antisymmetric, and transitive. We call it order. So what did we look about talking about order? We look at the Hasse diagrams, which are a cute way to represent typically small set, the ordered small set. And when we have a partially ordered set, how is this interesting to a computer scientist? Topological sorting. Many problems you need to do this. For example, every time you put together a car or a computer or some appliance, yes, I think we probably had some homework problem. We can go there and spend a minute on that. I think we saw this in algorithms, right? All right, so here we have an example. Oh, you are not seeing it. This is a Hasse diagram. Oh, you don't see it. So what is the meaning of the Hasse diagram? At the bottom, you put all the elements that no one comes before them. How are they called, these elements? Minimal. And then on top you put the one that are bigger than them, as little as possible. What do I mean by as little as possible? You cannot stick an element in between. bigger than the one below and smaller than the one above. So in this example here, there is no element which is bigger than 1 and smaller than 4. And then on top, you put the next letter. So you have no elements between 4 and 6. By transitivity, if 1 is smaller than 4 and 4 is smaller than 7, then 1 is smaller than 7. Yes?
What about when you mix up the orders? So if we're doing a traversal of this, like we were talking about, you're going over the section, you do 1, 2, or 3 as our first choice.
Yes?
Does that mean that those are all equal to each other because you can
No.
switch around the position? Okay.
No. They are incomparable. So you cannot say if 1 is greater than 2 or 2 is greater than 1. So we don't have this information.
So whenever you can intermix which value you mix, those two things are incomparable. I'm just trying to see.
Yes.
So that means that if we had chosen like 1, 2, 3, then 4 and 5 are incomparable with each other.
Yes. So in order to be comparable, either you go up one level or up many levels.
How does that work with multiple dependencies? So if we do 2 and because 4 depends on 2 things, 5 depends on 1.
Well, I wouldn't use the word depend, but go on.
But so how do you compare what's the relation?
The relation between?
Yeah, does that mean anything that 4 depends on 2 things and 5
No.
depends on 1?
No, but if these are tasks that depend on each other, then before doing task 4, we have to do 1 and 2.
Yeah.
I think we look at some example like baking a cake or something like that.
That makes sense.
There are steps. Yes.
There's some questions on the about that.
And so one problem when you have this, oh yes?
So sorry, just by the same logic, therefore 1 is incomparable with 5 as well.
Yes, the 1 is incomparable with 5. And so the problem here is to write this in order, in some order, such that you never write first an element that comes after another. So here you cannot write 4 before writing 1 and 2, because 4 comes after 1 and 4 comes after 2. All right? All right, so this is something that we do with partial orders. And so we look at partial order, we look at equivalence, we look at equivalence classes, duality with the graphs. So a binary relation and a graph are two sides of the same coin. What are the edges of the graph, how they are related to the binary relation? You have an edge from A and B if A is related to B. And so, now if we have to reason with the graph or we have to reason with a binary relation, maybe what we have to do is difficult if we look at it as a subset of the Cartesian product, becomes easier if we look at it as a graph or the other way around. And so we have this possibility of choosing which way we do the job. So for example, an interesting problem is to see whether a binary relation is transitive. We have a very interesting algorithm graphs that tell or check or construct the transitive closure of the relation. Many problems when you look at maps and when you want to go from one place to another, whether it is on the street or with the max or with an airline, a problem of this type. All right. I don't know if this is the level that we should look at this. We can have more details, but I think this is an overview with all the points. Probably is useful. See, many of these points you do for anything. You can have a very similar points when we talk about graphs, a very similar points when we talk about the trees. There is always a definition, there is always a notation, there are properties, there are operations that you do in that, and how this relates in the subject of this course. Yes?
Will the final be heavier on the topics we gotta get tested on?
Yes.
Will it be like 50% new stuff, 25% past, 25% this?
Maybe, yes. Kind of. I'm not sure how students are going to use this in practice, and now that you know that it's 25 rather than 30 or 20, which I cannot be that precise. But
How many questions?
same, 33. Yes,
If we can't make the final, get the,
say that again.
if we can't make the final, then we get,
No. So I counted the two best. So
missing just means
miss means that it's not going to be counted because it's not the best.
you haven't seen my schedule,
All right, so here you have the opportunity to ask anything you want.
Not the sort and give me the graphs from the homework.
The sort
Which one is-
of the graph of the homework. Let me bring the homework and then you tell me. This is the last homework, right?
Yeah.
The last homework. And which problem?
The one that says
Oh, sorry, you are not seeing it. Is this one here?
4 and 5.
4 and 5. So we have this graph. Should I rewrite it on my paper? So we reason about this. We have A, B, and C. Yes. Then I'll say that again.
It's still on the computer.
Yes, I want to copy it. Well, I can. You can look while I'm drawing here. We have D. We have E, F, and we have G. All right. So which one do we want to do?
It says which one is not.
All right. So let's go back here. Then we have to look at this one here. Which one is not a breadth first traversal? So let's recall what the breadth first traversal means. How is it a breadth first traversal? You start from a point, anyone you want, and then you connect all the ones that are one step away, right? Then you do all the ones that are 2 steps away and you didn't count yet. Then all the ones that are 3 steps away and you didn't count yet. If you have to code the program, this is not a good idea. But if you have to solve a problem this because it's not efficient. But if you have to solve a problem this way, this is the best idea. Also, if you write a program and then you want to test it, you compute the breadth first traversal in the way I'm telling you, and you compare with what the program did. So, let's write the first. We start from A, right? So, if we start from A, what are the one you get in one shot? BC or CB. And so far, the first one, I'm looking at the first one, is a good candidate, right? So, which one you get in 2 steps? D. And so far we are doing fine. And which one you get in 3 steps? E and F. And then G. So, the first one is a breadth first traversal. All right? So, let's do the second. We start from C. Which one you get in 1 step? A. In 2 steps? B. In 3 steps? In 4 steps? Here is the problem. Right? You have to get to E before G. So, this is the culprit. This is not a breadth first traversal. You want to check that the other 2 are? So, we start from E. In 1 step, we get what? D and G, fine. In 2 steps, F and B. And then you get A, and then you get C. So, this is the breadth first traversal. And so, I think the last one also is. So far, so good? Great. The next one. Not depth first. No, which is a depth first? Which is a depth first? So, let's say one more time what is the depth first. Depth first means that you start from any point you want, and you keep moving, traversing edges as far as you can without finding again what you found already. If there is a fork, which one do you take? It doesn't matter. You can take left or you can take right. When you get to the end that you cannot move any further, if there are still nodes that you haven't taken, what you do? You move back to the previous fork, the closest, and you take the other one. Alright? And so, we start from A. It looks like we can go to B and C. Here, we take B. Right? And now, what should we take next with the depth first? B. And so the first one is not good because now we forget the B and we move to C. So let's take the second. A, we go B, we go D, we go E, and then we take F. No good. Why? Because we still have G and F to take. So this is not good either. So the next one. A, we take C, that's fine. This is then the end. So we move back to A. Now we have a different fork to take. So we take B, then a D, that's fine. Then E, that's fine. Then G is fine. Then F is fine. This is it. Alright? Since we had the lecture, I added 2 links to a nice explanation of a breadth first and depth first. This is really an algorithm with all the details, done by hand, but with all the details. So that's a little heavy, heavier than we do in this way. But this is nicely explained, so we can go there and see the algorithm. Next question. Yes?
Just with homework 7, as far as the question pertaining to the removal of the group node.
Yes, let's go there and see how is it. All right, number 7. Yeah?
No, the number 8.
Number 8. All right, number 8. Do people see this one? Let me move it a little. All right, we have these 3. And we delete 5, right? So first, when we delete, we have to look at the different situations. So one situation, an easy one, is that this is a leaf, right? And then you just make it disappear. So there, if you delete 11, for example, you just take it out and you are done. The other one is when there is only one node, and then you pull up the only child that is there. This is not the situation, because every node here either has 2 children or 0 children. So it doesn't happen. And then there is the complicated case in which the node you remove has 2 children. So what is the rule in this case? Yes?
You have to take a successor, right? So you can use either the in-order successor or the pre-order successor. Yeah, for binding, either the in-order successor or.
All right, so I have a rule that I think is simple. My rule is that either you take the leftmost of the right child
Yeah, that's the.
or the rightmost of the left child. So basically, from the one you remove, you do 1 step left and then all the way right, or 1 step right and then all the way left. All right? And so here, if we go right and then all the way left, what do we find? 9, because we go right and then there is nothing to go left, so we already are all the way left. So 9 is a good candidate. In fact, if you put there 9, still remain a binary search tree. Yeah? Same if you go right, you go 1 and then you have to go all the way right, there is nothing to go. So 1 is a good candidate as well. So the rule is that you go left and all the way right, 1 step left and all the way right, or 1 step right and all the way left. So for today should we close here? So now I would like you to come here on Wednesday with problems of any kind. Homework, previous exams, problems that you make up. And you say, oh, this would be a nice exercise in an exam. No. Because this tests the knowledge of this property, fact, or definition. And it's easy to write and it's easy to solve. And it's not so easy to find problem where you can do this. In fact, I'm thinking to do a wiki that should be managed by students, where they say these are good problems, and then I put them in the exam, so my life is easier. I'm not joking. It's not a good idea. All right.